Okay, this is AP review quiz number 1, this multiple choice quiz. This is video number 4, and we'll be covering problems 31 to 40. A large number of randomized experiments were conducted to determine whether taking a particular drug regularly would decrease the chance of getting a certain disease. For each of the experiments, the drug effect is the difference between the proportion of people taking the drug who got the disease and the proportion of people taking a placebo who got the disease. If the drug had no effect whatsoever, this is important, which of the following experimental results would be anticipated? All right, so if it has no effect, we would expect to fail to reject, which means we'd have a p-values that would be greater than alpha, right? So we would expect our p-values to be greater than alpha, and p-value greater than 0.05, this is basically an alpha, for about 95% of the experiments. 5% of the time, we're going to reject incorrectly, but p-values should be greater than alpha. We would expect that to happen. So 1 is a definite, that's definitely going to be the case. I'm going to skip 2 and come back to it because it's a little more challenging. Number 3, probably the easiest of the 3 to understand. When 95% confidence intervals for the population drug effect are constructed, those intervals would include 0 about 95% of the time. And remember, if we include 0, there is no effect. Well, 95% of them are going to be right, and about 5% of them are going to be wrong. So 1 and 3. And at that point, we know it's going to have to be E. But let's talk about number 2, because it's a little more difficult to understand. There will be about an equal number of experiments showing positive and negative values of the drug effect. So let's just say the proportion of the people who in the population who get the disease, and I'm just making up a number, is 0.30. So 30% of the population gets a 0. Well, we're going to have some placebo above, some placebo below, some placebo above, some placebo below. All right. Well, I would expect for those who are getting the drug, I would have exactly the same numbers. So basically, there would be an equal number of experiments showing positive and negative values. All right. An equal showing is an equal percentage. All right. Some will show positive, some will show negative. Hey, they didn't. Some will show they did. But on average, it should equal out. So 2 is also correct. And our answer for 31 is E. All right, 32. As part of a class project at a large university, Amber selected a random sample of 12 students. So N is 12. In her major field of study. All students in the sample were asked to report the number of hours spent studying for the final exam. And their score on their final exam. A regression analysis on the data produced the following partial computer printout. Amber wants to compute a 95% confidence interval for the slope of the least squares regression line and the population of the students in her major field. Assuming the conditions for inference are satisfied, which of the following gives a margin of error for the confidence interval? We're going to go ahead and write the entire equation. So our entire equation is going to be b hat plus or minus t star times the standard error. Well, b hat, first off, this constant is going to be the y-intercept. And it'll either say intercept or constant. So this right here is my x value, and it's also my slope. So b hat is 2.697. That's my slope. Plus or minus, we'll come back to t star in just a moment. Standard error of 0.745. So there's my standard error. And now I need to calculate t star. Well, degrees of freedom in this case, our degrees of freedom are for regression is n minus 2. So 12 minus 2 gives me a degrees of freedom of 10. And we want to do a 95% confidence interval. And I know this time we didn't need to do it, but just practice. Second vars, inverse T, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom in this case are 10. And I end up getting 2.228. This part makes up my margin of error. So my answer to this one is A. While we're here, I also want to talk about slope. What is my slope in this particular case? I know they didn't ask us this, but we're going to do it. All right. Whatever they give me here is my x value. And remember, slope is y over x, technically the change in y over the change in x. So the denominator is study hours. And the score on the final exam. So I'm going to put this as their grade. All right. So for every 1 hour increase in study hours, we had a positive 2.697 increase in the grade. For every 1 hour 1 hour increase in study hours, our grade went up by 2.7 points. Okay, that's what that means. A mathematics competition uses the following scoring procedure to discourage students from guessing, choosing an answer randomly. On the multiple choice questions, for each correct response, the score is 7. For each question left unanswered, the score is 2. For incorrect response, they receive 0. And by the way, when we took the SAT and PSAT back in my day, you got points for being correct and you lost points for being wrong. So there really was a discouragement to guess. If there are 5 choices for each question, what is the minimum number of choices that the student must eliminate before it is advantageous to guess on the test? So we have eliminating 0, 1, 2, 3, or 4. So if we eliminate 0, that means we have 1, 2, 3, 4, 5 choices, one of which is correct. So we have the probability of guessing correctly is 1/5. And 1/5 times 7 equals 1 divided by 5 times 7 equals 1.4. And 1.4 is less than 2. If we left the thing blank, we got 2 points. So if we eliminate 0, the probability of guessing it correctly is 1 out of 5. We can't eliminate any answer choices. We shouldn't guess. We should get the 2 points. If we eliminate 1, well, now we have 1, 2, 3, 4 choices. All right. And the probability that we guess the correct one is 1 out of 4. And when we do that, we end up getting 1.75, which is less than 2. And once again, if we can only eliminate 1 choice, we shouldn't guess because we should just take the 2 points and go, that's good. If we can eliminate 2 choices, now we have 1, 2, 3 choices to guess from. It's like, all right, there's 3 choices. My probability of guessing is 1/3. And when I multiply that, I end up getting 2 1/3. 2 1/3, which is greater than 2. So the point that I can eliminate 2 choices, I should go ahead and guess. I shouldn't leave it blank. I shouldn't leave it blank and take the 2 points. I should go ahead and guess as soon as I can eliminate 2 choices. If I eliminated 3 choices, my probability of guessing correctly is 1/2. 7 times 1/2 is 3.5. Definitely better. So this is better and this is better. These are not. If I eliminate 4 choices, then I only have 1 possibility. And basically my probability is 7 times 1 over 1, which is 7 points, which is definitely better than 2. So if I can eliminate 2, 3, or 4, I should go ahead and guess. And they said, what's the minimum number? The minimum number I need to eliminate is 2. All right, number 34. The probability that a new microwave oven will stop working in less than 2 years is 0.05. The probability that a new microwave oven is damaged during delivery and stops working in less than 2 years is 0.04. By the way, this has an and here, that's important. The probability that a new microwave oven is damaged during delivery is 0.1. And we have, given that a new microwave oven is damaged during delivery, what's the probability it stops working? Well, I basically have two different things going on. I can have a damaged microwave, or I can have a microwave that stops working. As soon as I have two things, I like to go to my table. It's just a great organizational tool. I need to always identify numbers that only are associated with one variable. Given the oven will stop working in less than 2 years is 0.05. Well, that's obviously not contingent on anything. It just says it stops working. So not working, working, this is 0.05. Probability that it is still working in 2 years is 0.95. Then we have damaged in delivery, and then we have not damaged. All right. The probability a new microwave oven is damaged in delivery and stops working is 0.04. So not working and damaged is 0.04. That means this value right here must be 0.01 because they have to sum up to 0.05. The probability a new microwave oven is damaged in delivery is 0.10. That makes this 0.90. This has to be 0.06. And I know I didn't have to fill out the entire table, but this way I can check it out to make sure it all works out. So this plus this equals this, this plus this equals that. Going horizontally, the same things check out. All right, given the new microwave is damaged. So the given is that it's damaged. And we're going to look for the intersection. So given that it's damaged is 0.10. What is the probability that it stops working? Intersection, 0.04. So what do we have? 0.04 divided by 0.1 equals 0.4. So our answer to 34 is D. '35. Perchlorate is a chemical used in rocket fuel. People who live near a former rocket testing site are concerned that perchlorate is present in unsafe amounts in their drinking water. Probably go faster if they drink it. Maybe they speed, maybe they drive faster. Drinking water is considered safe when the average level of perchlorate is 24.5 per billion or less. A random sample of 28 sources in the area produced a mean perchlorate of 25.3. So that we got an X bar, a sample of 25.3. Which of the following is an appropriate alternative hypothesis to address their concern? Well, the null hypothesis is that mu equals 24.5. We assume that we're safe. The alternative is mu 24.5. Well, if it's less than 24.5, I'm happy, I'm safe. What I'm concerned about is if it's greater than 24.5. So D is my answer. All right. And be really careful. Never use sample statistics for your null alternative, ever. The 25.3 could be eliminated immediately. Okay. And once again, the reason it's not less than is because, hey, if it's less than, I'm safe. I'm only worried if it's greater than. My concern is if it's greater than. All right, the computer output below shows the results of a linear regression analysis for predicting the concentration of zinc in parts per million from concentrations of lead. So we're predicting zinc. So y hat is zinc. From our x is lead. And so that I got from reading that part. But I can find it elsewhere, and I'll show you in just a moment, okay? So my response variable, zinc. The other thing is, this is always my x, always. This line refers, this is my slope line, but this is my X variable. I'm going to tell you, students miss this problem, this particular one, over and over again because they won't go back and do basic algebra 1. Remember, slope is the change in y over the change in x. So basically, we have this. Zinc is our y. We know lead is our x just because it's there. And response variable also means that. Our x will always have a 1 when we're dealing with the slope. And this will go in the numerator. It's positive. So, which of the following is a statement, corrected statement of the value of 19 in the output? On average, there is a predicted increase of 19 parts per million in the concentration of lead. No, concentration of, this should be zinc for every increase in lead. No, that's wrong. On average, there's a predicted 19 parts per million in concentration of zinc for every increase 1 part in lead. This looks really good. I like this one. The predicted concentration of zinc is 19 parts. What? We didn't talk about fish. All right. The predicted concentration of lead is 19. Approximately 19% of the variability in zinc concentration is predicted by the linear. No, 82%. The R squared, the coefficient of determination. So our best answer is this. So 36 is B. 19 parts zinc for every 1 part in lead. All right. It increase, and by the way, because it's a positive relationship, as lead increases by 1, zinc increases by 1. If lead decreases by 1, zinc decreases. They move together. Make sure you notice that. All right, number 37. There were 5,317 previously owned homes sold in Western City in the year 2000. The distribution of sales prices of homes were strongly right skewed with a mean of 206,000. So we have a mean equal to 206, 274, and a standard deviation equal to 37,881. But they're telling us the right skew. If all possible simple random samples of size 100, so we have size 100, so n equals 100, from this population, and the mean is computed for each of these samples, which of the following best describes the sampling distribution of the sample mean? First off, the mean doesn't change. Well, that didn't help me out because every single one of them had the same mean. Oh, well. But then we're talking about the sampling distribution of the sample means. And n is equal to 100, which is greater than 30, greater than or equal to 30. So it's going to be normal by central limit theorem. So we're normal by central limit theorem. So in which case, D and E are gone. So now we need to figure out the standard deviation. Well, remember the standard deviation of X bar equals the standard deviation of the population divided by the square root of n. Well, that means 37,881 divided by the square root of 100. Some of you are doing this in your head, and that's fine. So 37,881 divided by 100, caret 0.5, and we end up getting 3,788. So the answer to 37 is A. And by the way, you could have just said square root of 100 is 10, 37,881 over 10, and that would have done the same thing for you. Okay, so that's 37. Number 38. A physician believes that the exercise habits of East Coast adults are different from the exercise habits of West Coast adults. To study this, she gathers information on the number of hours of exercise per week from a random sample of East Coast adults and a random sample of West Coast adults. Which of the followings might be an appropriate null hypothesis for the study? Well, I'm going to real quickly notice they say average all the way down. All right, because they say average all the way down, I know that we're talking about a mean. So we're going to look at a null hypothesis, mean of the East Coast equals mean of West Coast. And they're looking for different. And the alternative would be mean of East Coast does not equal mean of the West Coast. But they want a null hypothesis, so this is the one I'm looking for. So I'm looking for an equal statement. So the average number of hours of exercise per week for East Coast is different. No, that's the alternative. We want the null. The average number of hours of week per week for East Coast is the same. That's equal as the average number of hours per West Coast. That looks pretty good. I'm thinking B, I'm liking B already. The average number of hours of exercise per week for East Coast is greater. No. Remember, our null is always going to be an equal, so C is out. The average number of exercise is less, so no. The probability, well, that's probability. That's not a, that isn't even a null hypothesis statement. So 38 is B. Once again, please notice it's an equal. Also pay attention whether they're asking for the null or the alternative. This was a kind of a give me problem, but if you chose the alternative, you would have chosen this one, which would have been the first one. You would have gotten it wrong just because you misread it. Okay, number 39. For a roll of a fair die, each of the numbers is 1, 2, 3, 4, 5, or 6 is equally likely. A red die and a green die are rolled simultaneously. Oh my goodness, I'm rolling 2 dice. As soon as I'm rolling 2 of something or doing something over and over again, I need to make a sample space. All right, so I probably, if I'm really doing this well, I would go ahead and use 2 different colors, but I'm not going to because I want to go through this fast. So we're going to go red minus green. So 1, 1, 1, 2, 1, 3. And by the way, you should practice making this thing 3 times as fast as you can prior to doing the test, because that way, if it does show up, it doesn't take that long. And yes, I recognize this doing the sample space does take some time, but I guarantee that if you practice it 3 times, you'll probably have it down to less than a minute, which means each problem you have 2 minutes to answer. And obviously, if you do the sample spaces, people do really, really well on the problems when they make the sample spaces. When they don't make the sample spaces, they don't do so well. So the first number is the red number, the second number is the green number. Which of the following graphs best represents the most reasonable distribution? All right, just out of curiosity, I'm going to take the center section. I'm going to go this way. Because that's the most common thing that happens. 1 minus 1, 2 minus 2. Well, if I subtract those, I get 0. So that means my highest point should probably be in the middle. Well, that looks like C is going to be my answer real quickly. What happens if I have my worst case? Well, my worst case would be a small red and a big green. 1 minus 6 is -5. Oh, but it only happened once. This is -5. Over here, 6 minus 1 is +5. That only happens once. So real quickly, I can see that this is my shape. All right, so C is my answer. Now, how in the world did they get these values? They took the probabilities and multiplied by 500. Well, I look at this, I have a 36. So 1, 2, 3, 4, 5, 6. So 6 out of 36 times 500. And let's just see how close we get to 80, just out of curiosity. Next, recognizing that this is a simulation, so it won't be perfect. 6 divided by 36 times 500. And we see 83, and it's like, that's actually pretty reasonable. Okay. If we wanted to check the ones on the end, this is 1 out of 36. 1 divided by 36. We did it at 500, so times 500. And we would expect to have about 13 And sure enough, we're definitely under 20, okay? Anyway, 39 is C, becomes much, much easier if you do this because you can see 1 minus 6, negative 5. Oh, that goes here. 6 minus 1, positive 5. Oh, that's here. These represent 0, and that's the one that's most common. All right. Finally, number 40. The probability of winning a certain game is 0.5. If at least 70% of the games in a series of end games are won, the player wins a prize. It's not enough that you win, you have to win 70% of the time. Well, you're only expected to win 50% of the time. All right? If the possible choices are 10, 20, or 100, which value should the player choose in order to maximize the probability of winning the prize? The more times I play it, the closer it is to getting the actual value. So if I play it 100 times, I'm going to get really close to 50%. If I play it 20 times, I'm going to be closer to 50% than if I play it 10 times, or at least I expect to be. But I need to win it 70% of the time. So consequently, just from a logic standpoint, this is the one I should choose. But even if the logic doesn't follow, we can do this on a binomial situation. So they tell us our P equals 0.50. All right, our P is 0.50. Well, I have to win 70% of the time. Well, that means if I play 10 times, I can win 0 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But 70% of 10 means I have to win 7, 8, 9, or 10 times. If I win those, I win a prize. Otherwise, I'm a loser. All right. Well, I did not circle zeros, so this needs to be a 1 minus the binom CDF trials, that's my N, is 10, probability 0.50. Oops. And then I have an X value. I subtract out the highest thing I don't want. I don't want to win 6 times. I want to win at least 7. So let's try that out. Let's see what we get. 1 minus second vars, binomial, CDF, trials are 10, probabilities 0.5, my X value, highest one I don't want, 6 isn't enough wins. If I play it 10 times, I have about a 17% chance of winning. So if N equals 10, the probability I win is about 0.1718. Let's try it if we do 20. Well, if we have 20, we can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, ... all the way to 20. Well, what's 20% of 70? Or 70% of 20. So 0.7 times 20 means I would need to win it at least 14 times. If I win it 14 times, I win. If I win it 15 times, I win. I can win it all these times, and I'm still a loser. All right? Don't tell me I'm a loser. I'll get offended. 1 minus the binom, CDF. Trials this time is 20. The probability is still 0.50. My X value, I'm going to subtract out the highest value that I don't want. If I win 13 times, I still won more than half, but I needed to win 14 or more. So if I win only 13, I'm a loser. So 1 minus second vars, binomial, CDF, trials is 20, P is 0.5. My X value in this case was 13. And now my probability, if N equals 20, my probability of winning is 0.0576. That's clearly less than 10. So 20 is a bad choice. And if I made the same number line, I need 0.70 of 100, which means I need to win 70 games. So 0, 1, 2, ... 68, 69, 70, 71, ... 100. I have to win 70 or more times. If I only win 69 times, I don't get a prize. So 1 minus the binom CDF. Trials is 100. Probability of winning is 0.50. And this is 69. Because that's the highest value that I don't win with. So 1 minus second var, 1 minus second vars, binomial CDF, trials are now 100, my probability is still 0.5, and my X value is 0.69. And if I did that right, I did not. 1 minus second vars, binomial CDF, clear, my X value is 69. And I get a very, very small probability. If N equals 100, the probability of me winning 70% of the time is 0.0000039. Clearly, I have a much better chance at 0.178 playing 10 times. So I should only play it 10 times. Why? Again, the more times I play it, the more likely I am to get close to reality. Well, reality is 0.50. I don't want to be close to reality. I need to win 70% of the time in order to be a winner. So I need to play it as few times as possible if I want to have 70% win percentage. All right? It's kind of like this. A little kid, 3-year-old, shoots his first basket and makes it. And you're like, gosh, this guy's going to the NBA. It's fantastic. But then the next 20 times they shoot it, they don't make it. So it's not unusual for it to happen a few times that they make it. It'd be really unusual for them to make it all the time or a lot of the time. In this case, we expect to win at 50% of the time. It's unusual that we'd win at 70%. And the more we play it, the less likely it is that we're going to get to 70% if this is reality. If this is reality, we're really unlikely to get to 70% the more we play it. It's even less likely if we play it 1,000 times. All right. Thank you for watching.